Swayam Prabha. Digital India. Educated India.
In today's lecture, we will see some more topics on the area moments of inertia that we were discussing in the last lecture. The last lecture we saw how to determine the second moment of the area with respect to a given axis, and also we saw how to use the parallel axis theorem to compute these moments with respect to a centroidal axis and then with respect to an axis parallel to the same. Today we will see the concept of product of inertia, which is useful when we consider the rotation of axes. As we saw that if we have a theorem that relates the second moment with respect to two parallel axes, it becomes convenient to determine the moments when the object is translated. But now if the object is rotated, its moment with respect to the given axis also changes. But it will become difficult if every time we have to determine the second moment by integration. So we will see theorems that help us determine the second moment of a given area when an axis is rotated. And in order to compute that, we also need the concept of product of inertia. So first we define this product of inertia as, for a given area, if we consider this small element dA, which is situated at a distance of x and y from the axes x as well as y. Now we know that the second moment of this area dA with respect to, let us say, the x axis is nothing but y square dA, and the same way the second moment of this area with respect to y axis is x square dA. So the product of inertia of this elemental area dA with respect to this axis, that is OXY, is given as XY dA. So if we integrate this quantity, that is XY dA, for this domain, we get the product of inertia of the complete area, that is IXY. So IXY is determined as integration of XY dA. So if we consider areas which are having some axis of symmetry, let us say this area has an axis of symmetry OX. So it is possible to find these differential areas dA such that for each of the area dA we have a corresponding area dA prime, which is located at the same distance from this axis but in the negative direction. So the product of the inertia of this area is nothing but xy dA, and the product of inertia of this element is minus xy dA, which is equal to dA prime. So, it is possible to find for any differential element a corresponding element, because we have this axis of symmetry OX. So, the summation of this is 0, and thus the product of inertia for this element is 0 with respect to this axis OXY. So, this property can be conveniently used when computing the product of inertias for symmetric objects. So, let us see how to apply the parallel axis theorem for the product of inertia. So, here let us say we have determined this product of this area with respect to an axis OXY, then we are interested to find the product of inertia with respect to a centroidal axis. So, C being the centroid of this area, we have the parallel axes, that is x prime y prime, passing through the centroid. If the location of this differential element is x and y, they can be written as x bar, the location of this centroid, plus x prime, which is the location of this differential element dA in this coordinate system, that is y prime c x prime. Same way, the y coordinate can be written as y bar plus y prime, and thus if we have Ixy, which is nothing but integral of xy dA, we know that Ixy is nothing but integral xy dA, and x is nothing but x bar plus x prime. So, we write that, and if we simplify this, so let us write this, this is nothing but integral x bar y bar dA plus integral x prime y prime dA plus the quantity, that is integral x bar y prime dA plus integral y bar x prime dA. This quantity is nothing but the first moment of this area with respect to this centroidal axis. So, this quantity is 0, and the same way we will find that this quantity, which is again the first moment of the area with respect to the centroidal axis, it is again 0. So, these two quantities become 0, and so what we have is integral x bar y bar dA, which is nothing but x bar y bar, integral dA is the area of this element, and this quantity, that is x prime y prime dA integral, is nothing but the product of inertia of this area with respect to this axis, that is x prime y prime, that is the centroidal axis. So, the parallel axis for product of inertia is found in this way, but one has to be careful that this quantity can be positive or negative. We saw that in case of the second moments, the quantity is always positive, because we have y square or x square, and so whether the element is in the positive or negative direction of a given axis, the quantity is always positive. But in this case, this quantity is positive or negative depending upon the sign combination of the location of this centroid with respect to the axis that we have considered, that is y x. So, if the centroid is located in other quadrants, then this value will have appropriate signs. So, one has to note this point, that these values are measured positive from the xy axis to the centroid. So, let us take one example. Here you see a triangular lamina for which we are interested to determine the product of inertia. It is of height h and base b. We are interested to find the product of inertia with respect to the xy axis and with respect to the centroidal axis parallel to this xy axis. So, first we determine the product of inertia using direct integration, and then we use the parallel axis theorem. So, let us take vertical differential area strips. So, here we are considering a thin vertical strip whose centroid is located at this distance y bar element and x bar element, which is nothing but the x coordinate of the location of this element, and this distance can be found by knowing the height of this thin strip, that is y, and so y element is y by 2. And then we can integrate it between the limits, that is x from 0 to b. From the similar triangles, we have this y equal to h times 1 minus x by b. So, we have considered this triangle, say A, B, C, D, E. So, we consider these similar triangles, that is EAD and BAC, and relate this distance y and h with respect to this x and b. So, once we have this quantity, we can write the area of this differential element dA as y times dx, where y is this quantity h into 1 minus x by b, and knowing these two quantities, that is x element is x and y element is half of y, which is half of h into 1 minus x by b. Now, we can write the product of inertia of this thin strip with respect to the xy axis as dIxy, and then we integrate it between the limits, that is 0 to b, from this to this point. So, we have Ix as integral dIxy, which is equal to integral x bar element y bar element times dA. X bar element is x itself, y bar element is y by 2, which is half of h square into 1 minus x by b square dx into this area. Okay. So, now we simplify this and apply the limits. We have this quantity. After simplification, it is 1 by 24 times of b square h square. So, this is the product of inertia of the given triangle with respect to the OXY axis. Now, we can move to determine the product of inertia with respect to the centroidal axis. We know the location of the centroid of this triangle, and now we want to determine the product of inertia with respect to an axis x double prime y double prime passing through the centroid C. we know these values, that is the distance of this y double prime is 1/3 base and this is again 1/3 of h. These are available as standard values, or one can find it by the first moments of this area. And now we write the parallel axis theorem for the product of inertia, that is I x y, product of inertia with respect to the axis x y, is equal to the product of inertia with respect to the centroidal axis plus x bar y bar a, and this value is to be determined and we know this value I x y. So, we have I bar x double prime y double prime is equal to I x y minus x bar y bar a, and I x y we have just determined as 1/24 times b square h square minus x bar is 1/3 b, y bar is 1/3 h times the area which is half b h, and from this we determine the product of inertia with respect to this centroidal axis x double prime y double prime, and that is equal to this quantity, that is 1/72 b square h square. So, in this way it is possible to apply this parallel axis to find the product of inertia of a given area. Now, let us discuss what happens to this product of inertias when the axis rotates. As we developed the theorem for the parallel axis, now we are interested to determine the relation between the product of inertia for two axes which are rotated with respect to a point, and we will see that this product of inertia is useful when we determine this relation between the rotated axis and the original axis for finding the second moment. So, we have this axis O x y and this differential element dA. The product of inertia and the second moments of inertia of this area with respect to this axis are known, like we have the second moment of this area dA with respect to OX as y square dA, and when we integrate it we get the second moment for this complete area. Same way we can determine the second moment with respect to the axis OY, and also we can determine the product of inertia for this area for OYX frame. Now, we are interested to find the second moments for a rotated axis with respect to O, that is x prime y prime, which is rotated by an angle of theta in the counterclockwise direction. So, now we want to determine the second moments for this rotated axis. So, these values are known. Now, we want to determine the values I x prime, I y prime and I x prime y prime, that is the second moments and product of inertia for the rotated axis x prime y prime. So, now let us try to relate the coordinate of this area dA in this reference frame, that is OYX, and the reference frame y prime O x prime. In the reference frame y prime O x prime, the location of this area dA is x prime from the OY prime axis. this quantity x prime, this quantity x prime is nothing but x cos theta plus y sin theta. We find that this distance is nothing but x times cos theta and this distance is nothing but y sin theta, because we have this as y and this angle is again theta. So, this angle is also theta and so we have this distance as y sin theta. Same way we can write this y prime with respect to this x and y. So, we get this x prime as x cos theta plus y sin theta and y prime as y cos theta minus x sin theta, which is nothing but this distance minus this distance. So, if we substitute in the equations, that is for the equation of this ix prime, we have it as integral x prime square dA, and we substitute this value of x prime as x cos theta plus y cos theta, and if we simplify that we get this expression. And same way we can write the expression for I y prime and I x prime y prime. So, we have I x prime as I x plus I y by 2 plus I x minus I y by 2 cos 2 theta minus I x y sin 2 theta. And same way we get the expression for I y prime as I x plus I y by 2 minus I x minus I y by 2 cos 2 theta plus I x y sin 2 theta. That means, we are writing the expression of the second moment of this area with respect to the new axis as a combination or an equation that relates this I x prime to the I x, I y and I x y are the second moments and products of inertia of the original axis. So, these equations relate the second moments of this area in the rotated axis to the second moment of the area in the original axis, that is I x, I y and I x y. So, these are related to I x prime, I y prime and I x prime y prime. So, these equations are nothing but the equations of a circle that we will see a little later. We know that the product of inertia is the product of inertia of the z axis, that is the polar axis, is invariant when we rotate the object or the axis, or that is the sum of the second moments, that is I x plus I y is equal to I x prime plus I y prime, which is equal to the polar moment of inertia or the moment of inertia with respect to the z axis. Now, as we rotate these axes, the second moments keep on changing, that is this I x prime and I y prime, they keep on changing, but for a particular set of axes we will see that these values become the extremum values, that means they reach a maximum or a minimum value, because as we rotate these axes their distances corresponding to these axes keep on changing, and for a particular orientation we will see that the second moment with respect to these axes reaches the extremum, that is either they become maximum or minimum, and these are known as the principal moments of inertia, and the corresponding axis is known as the principal axis. So, let us see how we determine these principal axis and principal moments of inertia. In order to do that, we first see the equations of Ix prime and Ix prime y prime, which are nothing but the parametric equation of a circle. That is, if we try to plot the values of Ix prime y prime and Ix, we will get a locus corresponding to a circle whose center and radius are nothing but the average second moment of inertia, that is I average is Ix plus Iy by 2, which is the location of this center, and the radius of this circle is nothing but root of Ix minus Iy by 2 square plus Ixy square. So, once we plot this circle, then we can find that the second moment of inertia with respect to the x axis has extremum values at these 2 points, and they correspond to the principal moments of inertia. And even if we use the other set of equations, that is Iy prime and Ix prime y prime, they also lead to the same circle. And we will find that the center of this circle is nothing but I average, which is Ix plus Iy by 2 for a given axis, and R, the radius of this circle, is Ix minus Iy by 2 square plus Ixy square. And these 2 points, that is A and B, corresponds to the extremum values of this second moment of inertia, because we see that for those points the value of this Ix prime is maximum and here it is minimum, and these are the principal moments of inertia. And for these points we find that this value Ix prime y prime, or the product of inertia, becomes 0. So, for the set of principal axes, the product of inertia is 0. And what are these values? From this graph or this picture we get that this maximum value is nothing but I average plus this radius R, and this value B is nothing but I average minus this radius R. So, we have this I max and I min as I average plus or minus R, and we have the expression for I average and R. And these are the principal moments. Now, let us see, for a given axis, let us say this point M corresponds to the second moment of inertia Ix prime and product of inertia Ix prime y prime. So, this point M corresponds to the set of values, that is the second moment of inertia and product of inertia for a given axis, and as this axis rotates about O, this point moves along this circle, and for each point this x axis corresponds to the second moment of inertia Ix prime, and the y coordinate corresponds to the Ix prime y prime, or the product of inertia. So, let us say for a particular axis M corresponds to the point which is nothing but x I x prime and I x prime y prime, and for this point we will see that if we take this angle as 2 theta m, we will see later why we are taking this as 2 theta m, then tan of this angle is nothing but I x prime y prime divided by this distance, which is nothing but, from the geometry, knowing these values of I average and R, it can be found that it is equal to I x minus I y by 2. So, this tan of this angle is nothing but I x y divided by I x minus I y by 2. Why we are using this 2 is that the principal moments of inertia are located on axes which are 90 degree apart. That means, for any body, let us say if I take this body, if this axis, let us say this is the original axis x and y, and these are the axes corresponds to the principal axis, then they are at 90 degrees to each other. So, let us say this is the axis corresponding to the maximum moment, then this corresponds to the minimum moment, second moment, then they span 90 degrees. But on this diagram we see that this axis corresponds to the point A and this for B, we see that it is spanned by a angle of pi. So, though this here the axis is at pi by 2, on this diagram this point A and B are located at an angular displacement of pi radians. So, from this we know that this is twice the angle between the principal axes, and that is why we say that if the angle between two axes is theta, then the points on this circle are at an angular displacement of 2 theta. So, this equation gives a value of theta m that defines two angles 90 degrees apart, which corresponds to the principal axis of the area about O. So, one value corresponds to theta m, the other value corresponds to theta m plus 90 degrees. Let us take one example to illustrate how we find these principal moments and the axis of these principal moments. Here you see an area which is symmetric about this OX and OY. The various dimensions are given, and it is also known that the second moment of this area with respect to x and y are also given to you as 10.38 centimeter to the power of 4 and 6.97 centimeter to the power of 4. We are interested to determine the orientation of the principal axis and the values of the principal moments of inertia about O. In order to do that, first we have to determine the product of inertia, that is Ixy for this axis O y x. So, first we determine the product of inertia with respect to this xy axis by dividing this section into three rectangles. that is the rectangles corresponding to this area and this area and this area, and then we can apply the parallel axis theorem to find the second moments of or the product of inertia of these areas with respect to this axis, and later on we will determine the orientation of the principal axis and the principal moments. So, this will be our strategy. So, let us first compute the product of inertia. So, these are the three areas, that is 1, 2 and 3. The location of their centroids are given here, that is, let us say for this area 1 it is located at 1.25 centimeters in the negative x direction, and it is located at a distance of 1.75 centimeters from x axis. Let us tabulate these values and apply this parallel axis theorem, because we are interested to now find the product of inertia of these individual areas with respect to O, Y, x axis, but we know these values for each of the centroidal axis. That means for this area 1 we know the value I x y prime with respect to, I can say that this is x prime and y prime axis. I can say that I know the product of inertia with respect to this axis. Now I want to determine the product of inertia of this area with respect to this OXY axis, and then I sum up all this to determine the product of inertia of the total area. So, you please note that the product of inertia with respect to centroidal axis parallel to the xy axis is 0 for each rectangle. So, the product of inertia is actually 0 with respect to these centroidal axes. So, for the area 1 we have the area as 1.5 centimeter square, the location of the centroid as minus 1.25 and plus 1.75, and the product of this value, that is x y bar a, is given here. For this area 2 you can see that the location of the centroid is at O, that is 0 0, and that product becomes 0. The sum of this is minus 6.56. Once we know this value, we can determine Ixy as, actually this Ixy is equal to I bar x prime y prime sigma, that is sum of the products of inertia of all these individual areas with respect to their centroidal axis, which is 0. So, this quantity becomes 0 plus this sigma x bar y bar a, and this is the quantity that we have just found, and that is minus 6.58, and that gives the product of inertia Ixy of this complete section or area with respect to this OXY axis. Now, we can now move on to find the principal moments. We know this Ix, Iy, and just now we determined this Ixy as minus 6.56 centimeter to the power of 4. So, now we can determine the orientation of the principal axis and the principal moments of inertia by considering this equation, that is tan 2 theta m, where this angle theta m is the angle of the principal axes. Let us say this A and the axis which is at 90 degree, that is B, corresponds to the principal axis, and if this axis, that is BOA, is rotated by an angle of this theta m, then the values of this principal or the values of the moments become the extremum, and that angle is given by this equation tan 2 theta m is equal to minus 2 ixy by ix minus iy. Since we have determined these quantities, we can determine this value. So, one is 75.4 and other is theta m plus 90, which is 255.4 degrees. So, these two angles corresponds to the principal axes, that is 37.7 degrees and 127.7 degrees, because we know that the values that have been determined are 2 theta m. So, it corresponds to 37.7 degrees and 37.7 degrees plus 90 degrees, which is 127.7 degrees. Now, we can also determine the corresponding moments, that is the principal moments, from this equation, that I max comma I min is equal to I average, which is Ix plus Iy by 2 plus or minus the radius of that circle, that is Ix minus Iy by 2 square plus Ixy square. Knowing these values, we find that I max and I min are 15.45 centimeter to the power of 4 and 1.897 centimeter to the power of 4. So, this problem illustrated how we use this product of inertia and the second moment of inertia with respect to an axis to determine the second moments and product of inertia with respect to a rotated axis, and also the principal axis and the principal moments. Now, we will see another method, which is a graphical procedure to determine the second moments for a rotated axis, and this method we call as constructing the Morse circle and determining the second moments and product of inertia for a rotated axis. So, we construct this circle, which is the locus of the second moments and the product of inertia. We have already seen that this point x corresponds to, say, the second moment with respect to the x axis Ix and Ixy. So, along the y axis we have Ixy and along the x axis we have Ix. If we plot Iy, then that point corresponds to minus Ixy, and this is the value of Iy. So, this diametrical line xy corresponds to the second moment of inertia and product of inertia on this circle, which we call it as the Morse circle. And this diametrical line ACB, which corresponds to the maximum moments, that is the principal moments, lies along this x axis. And we know that if we rotate the axis by theta, then on the diagram the point moves by 2 theta. So, for a given axis, if BCA corresponds to the principal axis, then this angle is 2 theta m, or the theta by which we have to rotate to find the principal axis. It is possible now to use a graphical method by first constructing this circle and determining the required axes and values. So, if you are interested to find the second moments and product of inertia with respect to an axis which is rotated by an angle of theta in the counterclockwise direction, then on this Morse circle we have to find a diametrical line corresponding to a rotation of 2 theta, that is x prime y prime, this diametrical line that you see, which is rotated by 2 theta in the counterclockwise direction, and these points, that is x prime and y prime, corresponds to the second moments, that is ix prime and iy prime for that axis, and the product of inertia is given by the y coordinate, that is either this value or this value. So, that is ix prime y prime, and this circle can be constructed by first finding the average value, that is ix plus iy by 2 for a given frame, and then the radius of this circle is nothing but root of ix minus iy by 2 whole square plus ixy square. So, let us see this method. So, let us construct the Morse circle for this object, and for this axis, that is ox oy, the corresponding moments are the points x and y, that is this x corresponds to ix comma ixy, and this point y corresponds to iy comma minus ixy for this area and this axis oxy. So, for an axis x prime y prime which is rotated by theta in the counterclockwise direction, if we want to know the principal moments and product of the moments, we move on this graph by 2 theta, and we have these points x prime y prime giving the values, and from this diagram we determine that this diametrical line, that is ycx, has to be rotated by this angle to make it the principal axis. So, we rotate the axis oyx by half this angle, that is if this angle is 2 theta m, then we rotate it by an angle theta m in the same direction, that is here we see that this axis ycx has to be rotated by 2 theta m in the clockwise direction in order to get this BCA axis, and that is why we rotate clockwise direction by half this angle, that is theta m, and we get this axis O, B and A, the principal axis for this area. So, we see that a graphical procedure can be followed to solve this problem, and we will see one example. Let us take one typical engineering section, that is an L section, and a given axis, that is oyx, about which the values of ix, iy and ixy are known. So, in engineering convention we represent this section by this notation, that is L 152 by 108 by 12.7, which tells the thickness, the width and length of this section. So, we know these values, that is the second moment with respect to the x axis, y axis and the product of inertia. We are interested by this Morse circle method to determine the principal axis passing through this point O and the principal moments, and also we are interested to determine the values of moments and product of inertia for this rotated axis, that is x prime O y prime, which is rotated by 60 degrees in the counterclockwise direction. So, let us see how we solve this problem by the Morse circle method. So, first let us construct the Morse circle by finding the center and radius of the Morse circle. So, for this section we plot this point ix comma ixy and the point iy comma minus xy, which are the diametrically opposite points on a Morse circle. Then we can construct a circle passing through these 2 points graphically, or else we can determine these values, that is center and radius, and also construct it, but graphical construction is also possible. That means if we know 2 points which are diametrically opposite, then it is possible to construct a circle which passes through these 2 points. And from this, let us determine this principal axis and principal moment of inertia, and then we will find the product of inertia with respect to the rotated axis. So, this is our strategy. So, first let us plot these points ix comma ixy and iy comma minus ixy. So, in this picture shows the 2 points, that is ix, which is 7.24, and ixy corresponds to minus 2.54. So, x is the point corresponding to the second moment of inertia with respect to x axis and ixy, and the diametrical opposite point is iy comma minus ixy. Iy is 2.61 and ixy is minus 2.54. So, minus ixy is nothing but 2.54. This has been plotted in a scale of 10 to the power of 6 mm to the power of 4. So, now this diametrical line corresponds to the second moments and product of inertia for the given axis. Now, we can draw a circle passing through these 2 points. So, these are the values and we used it to plot this. Either we can use a graphical procedure, or we can find this value of this center and the radius of this circle. The center is located at a distance of I average from this O, that is half of Ix plus Iy, which is equal to 4.925 into 10 to the power of 6 in this case. Then let us find this radius, which is equal to this distance CD square plus dx square, which is the square of this radius, where CD is nothing but Ix minus Iy by 2 and this dx is nothing but Ixy, that is the product of inertia. So, we first find this value of CD, which is 2.315 into 10 to the power of 6 mm to the power of 4, and this value xd is nothing but 2.54 into 10 to the power of 6 mm to the power of 4. So, from this we determine this radius as 3.437 into 10 to the power of 6 mm to the power of 4. So, on this diagram we construct a circle with center at this distance, that is 4.925, and with the radius of 3.437. So, this is the corresponding circle. Now, based on this circle we find that these points A and B are the points corresponding to the principal moments, and the axis has to be rotated by this angle, that is, let us designate it as 2 theta m in the counterclockwise direction in order to get the principal moments. So, that means if this is the axis OXY, then we have to rotate half of this angle in the counterclockwise direction, that is theta m in the counterclockwise direction. So, let us determine first this 2 theta m from this diagram in order to find this theta m. So, tan 2 theta m is nothing but dx divided by CD. We have just now computed these values. So, from this we get 2 theta m as 47.6 degrees and theta m as 23.8 degrees. So, this axis OA is rotated by 23.8 degrees in the counterclockwise direction, and this axis OB is 23.8 degrees plus 90 degrees. So, these two axes corresponds to the principal moments of inertia of the given area. Now, we can also determine their values, that is the value of A and B by measuring this distance OA and OB, and from the measurement it becomes 8.36 into 10 to the power of 6 mm to the power of 4. This is also equal to I average plus R, and this I minimum is nothing but this distance OB. So, you can graphically measure this, or you can also compute it as I average minus R, which is 1.49 into 10 to the power of 6. So, now we have determined the principal moments as well as the axis through which these principal moments have been computed. We can also determine the product of inertia with respect to a rotated axis. Like we are interested to find the product of inertia with respect to an axis OX prime Y prime, which is rotated by 60 degrees in the counterclockwise direction. So, that means in our original diagram where we have this XCX as the diametrical line corresponding to OYX, we have to rotate counterclockwise by 2 theta, that is 120 degrees, and we get this axis, that is X prime C Y prime. Now, by measuring graphically the value of OF, which is nothing but the projection of this point X prime on the X axis and projection of this point Y prime on the axis is G. So, we can measure these values of OF and OG, which will give the second moment of inertia, and we can measure this height, that is X prime F or Y prime G, which is nothing but the product of inertia, that is IXY. So, we have this value as 3.437 into 10 to the power of 6 from this diagram. We know that this is the IXY for the rotated axis. We find this Ix prime, that is this value OF as 5.96 into 10 to the power of 6 mm to the power of 4, and Iy, which is OG, as 3.89 into 10 to the power of 6 by measuring it in this diagram which has been constructed to the given scale, and Ixy, which is nothing but Fx prime or Gy prime, which is equal to 3.28 into 10 to the power of 6 mm to the power of 4. So, these procedures illustrate how we can use this Mohr circle diagram to evaluate the product of inertia. So, in this class we saw how to determine the product of inertia and the second moment of inertia and product of inertia for rotated axis, and also we saw the concept of determining the principal moments of inertia and the corresponding axes.